Hello, hello. Hello, everyone. Welcome back to the stream. My name is PH, and we are going to be going over pair product, which is very similar to pair sum. This is going to be a very short stream today because I will go through it thoroughly, but this stream will be short. All right. So essentially, what we are doing is we are going to have two for loops. So we're going to have I and we're going to have J. And we're going to have like I. How many are there? 5. And it's going to be like 3, 2, 5, 4, 1. And then this is going to be J, 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 J. I and J. So essentially, what we're going to do is we're going to start off with the I loop. Start with I loop. And iterate through the lists. So it would be 3. And then what we're going to do is we're going to iterate as I. And then iterate through the list as J. So it would be oh my gosh. 3 and then 2. 3, 2, 3, 5, 3, 4, and then 3, 1. And then we just do that over again. I haven't really thought about that. Like, would it iterate? It finds the first thing, but if we told it to like go through everything, so for instance, like it did 3, so then if I wanted to do this again, the second indency, and it was like 2, then wouldn't it be like 2, 4, 2, 4, and then 2, 1? But again, it wouldn't add up to 8. It's 6, 6, and then 3. And then if it did 5, it'd be 5, 4, which would be 9, and then 6, and then 4 would just be okay. But anyway, that is kind of what we get. And in this case, this would be oh no, this is I'm still going off of the sum. We're doing the product now. So 3 times 2 is not 8, 6. 3 times 5 is 15, 3 times 4 is 12, and 3 times 1 is is 3. So we're going to have to go through 2 times 4 is 8. So it would have to go through here, which is, I'm assuming, yeah, it would be, gosh, gnosis. So this would be, it would be, yeah, this would be 0 index. numbers 0. What am I doing? I could just put like numbers 0. And then numbers 1. So yeah. So in this case, it's 1, and then so it'd be 1 and then 0, 1, 2, 3, which would be, because I can't do. Why did I do that? Yeah, I forgot. Or I'm okay. So yeah, 2, 5, 2, 4, 2, 1. I don't know why I did that. Okay. All right. Let's just copy this. Let's close that. I'm kind of seeing how like we are using kind of the same brute force method of solving this. However, it's kind of the same problem over and over again. And I think that is what Shakti is trying to like explain, or trying to like, that's the whole premise of this, is like it kind of is the same problems, but it's just, and the same concept. It's gonna just be different things. So yeah. So let's just return something, and let's just copy these edge cases, and okay. So we are going to iterate through numbers as I, using range. All right. So for I in range of 0 and the length of numbers, and I'm gonna print numbers in I, just so we can see something. Okay, well, forgot, we can't just be doing wouldn't this just be easier doing that instead of like doing it for all of them? So let's try again. Let's close this and then do it again. So yeah, 3, 2, 5, 4, 1. So we're gonna do that again. And J in range of, again, it's just kind of the same problem as before. So it's 1 now, and we're going to, or we could put BI plus 1 and then the length of numbers, which we could print out, do an F string. So I would be I, and J would be, wait, what am I doing? Yeah, it needs to be this. So yeah, be 3, 3, 2, 3, sorry, yeah, so this wouldn't gonna start at 3 again, so it'd be 3, 2, 3, 5, 3, 4, 3, 1. If if I does not equal j, oh my gosh, and if I times j is equal to target product, then we're going to return I and j. My gosh. Let's print I. Jeez. Yeah, let's close that. So yeah, it would be. Oh no, we need to do the. Gosh, we went with the index, not the number. All right, let's close that again. And ooh. Hmm. Why is it? Let's try this one. Because if it's just, then we just need to subtract it from the index. Let's try it again. What? All right. Wait, is it because you can't do it there? Wait. Wait. It's stopping. Oh my gosh. What am I doing wrong? Yeah, it's not going. Yeah, the return is not working. Do I need a tuple, bro? What is this? Yeah, what the? It's the same problem. Bruh. All right. Kind of slow. Nope. It's still doing. Let's just do this. I don't think this is gonna work, but no. I'm really confused. This should be the same problem. Okay. Comparing to this. Okay. Yes. We're not really. Yeah. This is why I need to get better at debugging my own code instead of. Here we go again. Not debugging my own code and looking at the solution. Ay. Well, it's my solution, but still, I need help with. Yeah, we'll get there. Okay. Let's see where. Again, this would be better if I just wrote out pseudocode, but well, we're going to do that now. So we're going to iterate through numbers as j using range. Okay. Check if I is not equal to j and if the indices of I and j are the product of target product. That's a lot of words. Then, so this is where I was messing up. Just return a tuple of I and j. Because I was doing, oh my gosh, I was doing the actual value, the value within the indice instead of the index itself. So that's why. Okay, let's just do it again just to be sure. Oh, because and then we can work on the complexity. Yep, okay. So time complexity is equal to O. Oh my gosh, big O of n squared. Because again, we have to go through each, we got to go through I, index of 3, then do 2, 5, 4, 2, 5, sorry, 3, 2, 3, 5, 3, 4, 3, 1, then 2, 5, 2, 4, 2, 1, 5, 4, 5, 1, 4, 1, and then check all of that. So that is going to require a lot of checking. Again, we're not like really moving anything, but we're just checking, but that still takes time. But in recording, again, the same problem. I'm assuming it is O of, it's a constant. All right, let's. I think they're using like hash map to do this, so obviously it would be much better, but since I'm doing it in such a brute force way, let me just ask Google. Are my complexities for my brute force solution correct? Ooh, I didn't even type it in. Okay. Ooh. I don't even. Ah. My gosh. Bruh, that took so long. Yes, your time complexity analysis is correct, and the space is also accurate of n of 1. The outer loop iterates through each element of the list, which is n interactions. The inner loop iterates through the remaining elements of the list, starting from the current index. Since the number of iterations in the inner loop decreases each iteration of the outer loop, the overall time complexity is calculated as n plus, yeah, which is equivalent to O of n. Oh, big O of n squared. Space complexity, the algorithm uses a few variables I and j to store indices, which takes constant space regardless of the input size, making the complexity of making it constant. Nested loops usually result in a quadratic time complexity. When an algorithm only uses a fixed amount of extra memory, regardless of the input size, the space complexity is O of 1. So what? What did I just do? Bruh. Oh, I'm dumb. So two nested loops are usually quadratic. And minimal pointers in memory are usually constant. Again, I think I should just go over how this works. Here, let's just try it, because this position is the same one, because it's the same problem. Let's just look. Okay, so numbers, product. So they're using a hash map or a dictionary. And so these are the iterable things that we're looking for. So I and n. The index in the number in enumerate is it's a method that checks for I'm not gonna mess this up. So I remember it saying that yes, it built-in function that allows you to iterate over iterable like lists and strings, and so arrays, tuples, with while also keeping track of the indexed. Correct. So yeah. So this will iterate. Sorry, this will iterate over this, which is an array or list, and the complement, which is in set theory, it is the offset of. So I was looking that up yesterday. So in this case, let's just go down here. The complement is what's not in there, if I'm getting this correct. So once we have the 3 out of the equation, this is what we have. And finding the complement would be finding the difference between, if I'm correct. What is the definition? Gosh, of a complement in set theory. In set theory, the complement of set A is the collection of elements that are not in set A, but are part of a larger universal set, essentially. Right. Okay, so I just explained it backwards. So so what we're trying to find in this case, it would be 1 and 3. So yeah, so indexes of 1 of of 1. Sorry. Oh my gosh. Which is basically 0. Gosh, what is it? 2 and 3. So 0, 1, 2, 3. So 2 and 4. So right, and the complement would be whatever we don't have. So this is completely wrong with it. Well, I think it said it right, but I don't think I wrote it right. So yeah, so it would take out, so in this set, this is U, and then in A would be in this case, we're trying to find 8. So 3, that's 6, that's 15, that's 12, that's so 2. Yeah, so it would be 2 and 4. and whatever the complement. So A, this would equal 3, 5, and 1. Okay. So that in the complement, so again, this is just the naming convention. I don't know why I went that deep into. So we take the target product and we divide it by the num, which is okay. So then if I did print I index and num, freak, I have to do all this out. Hey, so yeah, if I did right, so if I did that, it'd be the index. Oh my gosh, I need to write this out better. So it would be that, and then the value would be the num. Which then I have to do that. So let's go down again. Oh yeah, we should take out all those large ass numbers. Jeez. Okay, so this is the index of 0, and it has the value of 3. So yeah, 3, 2, 5, 4. Why is it going over 1? 0, 1, 2, 3, 4. Yeah, why is it not going over 4? Is okay. All right, so the target product divided by the num. So it would be 8. So 8 divided by the num. Oh my gosh. 3. If the complement in the previous num, if 3, 8 divided by 3, which is like 2 with a remainder of, let's do that, 2. If the complement in the previous return the index in the previous number's complement. Oh. So we're just going through all of these things until it's divisible by that number and we get a number. So if the complement in I want to see what this is. Wait, hold up. Let's delete that. Wait, let's too many times. So the index would be 3. So 0, 1, 2, 3. So, bruh. So it'd be 8 divided by 3. This thinks this might help my brain more. Index of 3. So 0, 1, 2, 3. So yeah, index of 3, it's 4. And then the complement would be 1. Yes, because 8. What? Also, let's just do the complement, because I'm very confused as to how this is actually. Let's delete that. Let's do this. So this is the index. This is the number. The complement of 8, yeah, would be 2. But then we take the previous number and we push it in to the index of 1. I'm very confused on this. Then we do 2 again. So we go to 2. So our index of 2. So 0, 1, 2, 5. 8 divided by 5. What? No. It rounds up to 2. 5. Let's just do, oh my gosh, yeah. Why don't we just do that? It's like, this is kind of confusing me as well, because I don't know where it's ending and starting. Let's delete. Zero, 1, 2, 3. Oh, I get it now. Okay. I get it now. All right. Yeah, that is easier. Okay. So at this point, I get it now. Wow. That is way more efficient. Wait, let's delete that. Yeah, that's way more efficient. Wait, let's delete this one. Oh my gosh. Let's just delete all. I get it now. All right. Let's delete that. Let's do this again. So yeah, it goes 3. You get 3, which is the index of, oh my gosh. Let's move that over here. Aye. All right, so yeah, 3 with the index of 0, 3 with the 3 with an index of 0, the value of 3 at index 0, the value of 2 at index 1, and then the value of 5 at index 2. But also we could just... But wouldn't this end immediately as soon as I run this? It won't run. Yeah, because it's not in the thing. Okay. 0, 1, 2, 3. Would be 2. Okay. I get it now. I get it. All right. Let's start from the beginning so I can like kind of explain in my brain. So we get the index, we get the num. We are going to iterate through this. We keep the index. It iterates through an iterable thing like an array or list, and then it keeps track of the values. If the complement in previous nums, if the complement if the complement is in... If I guess in this case it's negative, it's 2.0. If 2.0 is print return the index, of of where we're at. So it'd be 2, which would be the index of 1. And the previous number's complement. I had it up until here. Now I'm like, what? This is 2. Previous number, but it's empty. Okay, my brain is super tired. Let's just...
Hey programmers, Alvin here. Right now, let's go over the approach for this.
I think I get it, but I'm just not understanding this.
Core pattern. And we'll jump right into the most efficient key to victory is going because the keys
All right.
of this dictionary are going to be
Okay, let's go.
my list. Because a Python written, I know the key to victory is going to be to use a Python dictionary to store previous numbers I've seen inside of my list. Because a Python dictionary gives me a constant time lookup, right? So I'm going to call this dictionary my previous nums, make it empty. Keys of this dictionary are going to be numbers inside of the list, and the corresponding values are going to be the index where I can find that number. So now what I want to do is just iterate through every element of the numbers list. So I can say for num in numbers. But what I want to also access is the index, because remember, I want indices to be the values of this dictionary. And so I'll use enumerate here. So if I enumerate these numbers, I can then have access to the index as well as the number itself. And make sure you spell that right. There you go. Cool. So just to get the ball rolling on this one, I'm just going to implement the number storing logic for my dictionary. So that would look something like this. As I hit my numbers, I want to add them as keys of this dictionary. So use num as the key, make its corresponding value the index. Nice. Now that you have this code, you can solve your main problem, right? Since I want to find a pair of numbers who have a particular product, that means multiplication, right? I want the inverse of that right now, which would be division. So to get my complement value, what I'll do is take my target product and divide it by the number. So this complement would contain a number that would pair up nicely with num. And so if complement is inside of the previous num's dictionary, that means I have a valid pair. So return a tuple of their indices. Remember, a Python tuple is parentheses, right? So for that tuple, go ahead and throw down your index, which would be where you found this current num, but you also want to pair it with the index where you previously found the complement. Luckily, I would have stored that as the corresponding value of that. So if I key into my previous num's dictionary, and I use complement as my key, this expression will give me back the very nice index of that complement. So that's good to go. So let's go ahead and give this a test run, and this should be our nice linear time, linear space solution for this. Awesome.
So essentially, from what I got,
Should be where you
is
found
that this is going to find, this is going to be, the complement is we're going to that index of, we need the complement. We're going to divide that, which then we would, if it's in here already, then we will go to, we'll return the index of where that was, which is 3. So the index would be 3. So it's 0, 1, 2, 3. So it's 4. We're at the 4. Okay. And then we go to the previous complement, and we go back to where the complement was, which was the index of it, which is 1, which is 4. And okay. I'm like, what? Again, this is way more efficient than what I'm doing here. It required less code. Again, I think I should start using dictionaries more. I just was like, I'd rather just do something that I know how to do versus, I was still struggling with this. I was like not getting, I was like putting the actual index. Sorry, I was doing the value instead of the index. Or was I doing the opposite way around? I was fucking up here. So, but I get this now. But it's way better. And but right, he was saying that this would be way, because O and big O of n squared again is it's linear, and then it's quadratic, I think. Yeah, and then I think it's polynomial, and then it's exponential, and then it's, forgot the last one, but I'm gonna have to like go, I get it, but I want to like know how to write this myself. Yeah. I did say this was going to be a short video, but it actually turned out to be the same length that as it took the other problem. So, but now I said that I would go over this problem, and I did today, but I need to go over it again and then write it out for myself and then break it down further. But thank you guys for watching. Other than that, that was I get it. Tomorrow, I think we're going to be going over uncompressed. And uncompress, so uncompress, compress, check in, and then we'll get through array of string, and then we'll start recursion, linked lists, binary tree, graphs, dynamic programming, stack, exhaustive recursion, and a mixed recall. Long way to go, but I think once I get the basics down, then and actually use like more time and space complex, like efficient time and space efficient, like ways of solving problems, this would be better. Okay. Anyway, thank you guys for watching, and I'll see you tomorrow.